Hello and welcome. For those of you who are learning MacLeod series in school right now, you will be familiar with the line over here in yellow, and that is the sine function can be approximated using an infinite series of polynomial terms. Okay, you might be thinking, okay, so what's the use of that? You need to remember that a long time ago, when all this mathematics was invented, nobody had calculators. So if I wanted to find out, say, sine of 0.1 radians, it is actually very difficult to do, right? If you don't have a calculator, you would really have to draw a really large triangle or draw a really large circle and then try and calculate. 0.1 radius is a very small angle, okay? And then it is actually quite tedious. So instead of doing all that work, well, you can use the MacLeod series. Just substitute x equals to 0.1 into each of these terms over here, and you get to the answer very, very quickly. And that is because 0.1 is a very small number, and when you have 0.1 times 0.1 times, raise it to a certain power, it becomes very small very quickly, and we talk about convergence, right? It converges to the answer you want, okay? But there is a limitation of MacLeod, and that is, you can see it is a summation of terms. It's an addition or subtraction of terms. What if you could improve on this? What if you can write sine of x as an infinite product, right? As an infinite product. Maybe that will converge faster, and that's what we're going to talk about today. Okay, we're going to try and write sine of x as an infinite product instead of an infinite sum of terms. Okay, so it looks like a daunting task, but let's start with a very simple story, a simpler problem, and that is, say, for example, if you like to eat durians, and durians can get a bit pricey, okay? So you do your homework, you actually jot down the prices of durian over a season of the durian, and then you plot out the points on a graph like that, okay? Next, you want to join up the points with a smooth graph, and voila. Okay, at this point, I must state that everybody knows, right, that you can't model the prices of durian using quadratic functions, but let's just bear with me for the sake of this exercise. Let's just say if it does, okay? Then once you have this drawn out, you're quite happy, but you actually want to predict the prices of durian. It would be great if you know the exact equation of function that draws this graph, because if you know that function or equation, you can substitute values of x inside and predict future prices of durian. And if prices of durian are going down, you want to buy more. If prices are going up, then you probably want to stop buying, right? So how do we find out the equation of, say, any graph that we come across? And I can hear some of you say, use the roots. And you're absolutely right, because the roots are the defining features of a graph. Let's take a look at the roots over here. The first root on the left is negative 1.667. That's negative 5 over 3. And then the other one is 1. Okay, with that, I managed to draw a green quadratic graph, okay, that cuts the graph, the x-axis at the same points as my durian graph, but the shape is nothing like it. What can I do to change the shape, okay, of my green graph? I can include an adjustment factor, A, right? So as you multiply higher and higher numbers, your quadratic graph gets more and more steep, more and more narrow. And I'll say the sweet spot is 3. And you can see the green and the blue graph are one and the same now, okay? Which means I can actually work this out on paper. What is my exact equation? And this is the equation that is going to predict the durian prices. Okay, back to decimals, you can see that the actual equation of the graph that I use over here is, exactly 3x squared plus 2x minus 5. And this is how we can approximate functions using roots. And you might be a bit confused, like, why are you saying approximate? You got the exact equation, the exact function. Now don't forget, our main problem today is to tackle this monster over here, sine of x. Sine of x is a periodic function that starts from negative infinity all the way to positive infinity. Okay, we are not going to be able to get the exact function. We're going to approximate it, right, using a series of terms. So that seems to be quite a daunting task. Why don't we limit, look at a small section of the sine graph. You get a nice short little segment here. That looks like a cubic graph. Yeah, and you can see we have 3 roots to work with: negative pi, 0, and pi. So I'm going to use the same technique as before. Okay, and you see a very nice blue quadratic graph, okay, whose orientation is the same as my red graph. That's very nice. Now to include my last root, that's x minus pi. Okay, but when I type in this root, you realize the orientation of the graph is wrong now. Okay, let me just zoom out to show you. Yeah, the orientation is wrong. So what I need to do to reverse the orientation is to multiply my entire blue graph by a minus sign, a negative 1. And very specifically, I'm going to apply this negative sign to the last root, right? Because you remember, right, this was the one that screwed everything up. Yeah, before that it was fine, right? When I introduced x minus pi, then the orientation went wrong. So clearly, maybe I need to change this guy to pi minus x. So there you go. Okay, now we have the correct orientation. I just need to scale the graph down using an adjustment factor. We get kind of a nice approximation, yeah, of the sine graph for just one cycle. But you might be saying, hey, look at the turning points. The blue graph is not a good approximation of the red graph. And I agree. So what you might want to do is maybe, okay, let's reduce it a bit more. And you can see that if you were to want to get, it's really hard, right? You want to get somewhere closer to the turning point, then the center becomes off. Like this region is no longer good. So we have to make a decision. And I made the decision, okay, and you find that this is consistent with MacLeod's as well, to get a better approximation of the center where x is equal to 0. I prefer it to be more accurate, right? Have a better approximation at the area around x equals to 0. Right? In fact, if you use calculus, right, you will know that the value that we actually want is 1 over pi squared. Right? You can work this out yourself. Right? You can pause the video and try. Okay? See if you can reason this out. Why is the constant adjustment factor 1 over pi squared? Hint: you should find the gradient of the red graph, sine of x, at x equals to 0, and the gradient of my blue graph at x equals to 0. Compare the two of them together, you should be able to work out what the constant is. Okay, very good. So what happens when we approximate with more and more terms? So let me just very quickly show you. So I've done it over here. This, by the way, have I said the name? Weierstrass factorization theorem, right? This, using roots to sort of approximate the graph, is a very, very simplified version of Weierstrass factorization theorem, okay? The full theorem works also for complex functions, okay, so which I'm not going to talk about here, right? So if I use one term, hey, remember the turning point is kind of off, but when I use 2 terms, aha, my second graph is in green. Right, let me just toggle on and off. Can you see the green graph? With 2 terms, it gets closer. Okay, let me turn off 1. Let's compare 2 and 3. 3 is even closer now, okay? Yeah, then I'm going to compare 3 and 4. 4 is even closer, and as you expect, when you approximate with more and more terms, it gets better and better. Now let's look at algebraically what this looks like. Okay, so this is what it actually looks like. We are taking sine of x to be approximated as infinite product. So here's my first root, x, right? And then my next root is x minus at negative pi, right? X minus negative pi, and then x minus pi, but we flip it around to get the correct orientation, okay? But I need to adjust these 2 terms with adjustment factor here, okay? If I have to include more terms, I need another adjustment factor. Include more terms, I need another adjustment factor. And you can sort of see a pattern going on. It's kind of like, if this is 1 pi, this is 1 pi, this is 1 pi. Okay, if this is 2 pi, this is 2 pi, this is 2 pi. This is 3 pi, this is 3 pi, this is 3 pi. Yeah, so I can write this. It's kind of like, remember we wrote a sigma and then we can replace certain things with a r or an n and sum from r equals to 1 all the way to infinity. I can also write this down as an infinite product. Okay, but first of all, one thing that I want to take note is this is x plus pi, this is pi minus x. I can also write the first term as pi plus x, and then we have pi plus x and pi minus x. That is the factorized form of difference of 2 squares. A plus b times a minus b is a squared minus b squared. So this can be written as pi squared minus x squared. This can be written as 2 pi squared minus x squared, so on and so forth. All right, so let's write this down. So the infinite sum is a capital sigma. The infinite product is a capital pi. So capital pi is written with straight lines, no curly leg for the pi. Okay, and to simplify this even further, you might be able to see that I'm going to multiply this adjustment factor into each of the two terms inside the bracket. And this is the final form of the infinite product that will approximate sin x. And just to let you know, I've also, in my Desmos graph, which I'll be sharing under the descriptions of the YouTube link, I've also included Maclaurin's approximation up to 5 terms as well. So you can click around and see, right? But before you click, which one do you think actually approximates the graph better? Weierstrass approximation or Maclaurin's? So this is part 1 of the video. In part 2, I'm going to show you how a famous mathematician made use of these two things, Weierstrass factorization theorem and Maclaurin's series for sin of x, and he used it to solve a problem that was open for 90 years. Right? Many mathematicians have tried, but none has succeeded except for this guy. Okay, it's the famous Basel problem. So I hope to see you in the next video. Until then, catch you on the flip-flop.